Assalamu alaikum. A very good morning. Today we are going to start the seminar, hybrid seminar on climate change and environmental sustainability, a multidisciplinary approach to energy for climate action. To begin this seminar, I would like to recite the Holy Quran, start the program.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم خلق الإنسان من صلصال كالفخار وخلق الجان من مارج من ماء فبأي آلاء ربكما تكذبان رب المشرقين ورب المغربين فبأي آلاء ربكما تكذبان آمنت بالله صدق الله العظيم.
Jazakallah. To introduce the seminar, I'm Mohammed Tufela, Program Officer at Comstech Secretariat, Islamabad. It's a pleasure to welcome you all. Today's seminar on the climate change and environmental sustainability, a multidisciplinary approach to energy for climate action, which is being organized jointly with the OIC General Secretary and the OIC Comstech. To discuss the climate change has emerged is one of the most critical global challenge of the century, affecting environmental systems, economic development, social stability, and public health, agriculture, biodiversity, and human survival. Rising global temperature, extreme weather events, sea level rise, deforestation, water scarcity, and ecological imbalance are increasingly threatening sustainable development worldwide. Sustainable development seek to balance economic growth, environmental protection, and social equality in order to meet the present need without promising the ability of the future generation. This relation between the climate change and sustainable development is deeply interconnected. Climate change itself undermines the sustainable development goals by increasing poverty, food insecurity, health risks, migration, and economic instability. Addressing climate change requires a multidisciplinary approach involving environmental sciences, economic sociology, political science, technology, agriculture, public policy, and global governance. We are meeting an important moment when the effects of climate change are no longer distant predictions, but lived realities. Rising temperature, extreme weather events, and resource pressures demand more than isolated solutions. The call for collaboration across the disciplines, from science and emerging to policy, economic, and social innovation. This seminar, hosted here at the OIC Comstech, bring together experts, practitioners, explore how energy's production, distribution, and consumption can become the powerful drive for the climate action. By integrating knowledge from the different fields, we aim to uncover practical, scalable, and just pathway toward the environmental sustainability. Over the course of today, we all hear insights, share experiences, and the most important, to identify actionable step forward. In this regard, I would like uh, His Excellency Professor Dr. Muhammad Iqbal Chaudhry. Unfortunately, he is not here. He sent us the recorded welcome address for the welcome address of this seminar. Professor Iqbal Chaudhry.
Billahi Minashaitan Rajim, Bismillah Rahim, His Excellency Ambassador Aftab Ahmed Kokar, Assistant Secretary General OIC Jeddah, Honorable Professor Dr. Ziaur Rahman, Director A.Q. Khan Institute of Material and Emerging Sciences, Department of Chemistry, Quaid-e-Azam University, Islamabad, Honorable Professor Dr. Ibrar Shibari, Associate Professor, Center for Interdisciplinary Research in Basic Sciences, Department of Environmental Sciences, International Islamic University, distinguished guests, esteemed faculty, researchers, and students. Assalamu alaikum wa rahmatullahi wa barakatuh. Ladies and gentlemen, a very warm welcome to our seminar on climate change and environmental sustainability, a multidisciplinary approach to energy for climate action. Climate change and environmental sustainability are often spoken of the same breath. Yet, they are not identical. Climate change is the accelerating crisis, while environmental sustainability is the enduring solution we must build. Bridging these two concepts require energy which sits at the intersection. How we produce, distribute, and consume energy determines whether we deepen the crisis or forge a sustainable path forward. A rapid increase in the global human population has intensified pressures on the long-term viability of modern civilization, primarily through deteriorating energy shortages and environmental degradation. In response, governments and researchers are actively exploring green and clean technologies as practical solutions. Water pollution has emerged as a critical threat as industrial waste and human activities contaminate drinking water sources, leading to serious public health challenges. At the same time, carbon dioxide emissions from burning of fossil fuels are driving global warming, calling for urgent action. I want to begin by acknowledging that we gather here at a very critical stage where the science is clear, the impact are accelerating, and yet our response remains fragmented. That is precisely why we have chosen multidisciplinary approach today, because climate change is not merely an environmental crisis, it is an economic, social, technological, and policy challenge all at once. And energy lies at the very core of this important net. Without this multidisciplinary approach, we risk solving one problem only to create another, such as deploying mining for battery minerals and devastating local ecosystem, or building hydropower that displace entire communities and ecosystems. Therefore, our discussions today must bridge these divides. Let the scientists speak to the urban planner. Let the renewable energy entrepreneur listen to the rural farmer. And let every one of us recognize that climate action is ultimately an exercise in collaboration across the disciplines. The challenge is immense, but so is the opportunity to build better, cleaner, more equitable and more resilient energy system that power our lives without endangering our planet. Ladies and gentlemen, OIC Comstech is working at the interface of various disciplines, and we are focusing on climate change and ecosystem restoration. With our partnership in different continents and different disciplines, we have launched many programs for smart cities, eco-friendly code security systems, and many other very important facets of climate change. I wish each of you to engage across disciplines. Challenge your own assumptions and leave the seminar with not just knowledge but concrete partnership and actionable commitment. Thank you very much.
Thank you. Thank you very much for the welcome address of the High Excellency, His Excellency Professor Dr. Muhammad Iqbal Chaudhry. He is the Coordinator General of the OIC Comstech, a distinguished national professor and the Senior Honorary Advisor at the International Center of Chemical and Biological Sciences, University of Karachi. He is also serving as a Vice President of Central and South Asia. His remarkable academic record include more than 1,530 research publications with over 51,000 citation and H-index of 990, an I-index of 1,083. He is also the innovator of 95 patents, including the 64 US patent, and has authored and edited 98 books and 40 books chapter published by leading American and European publishers. In addition, he has supervised more than 110 PhD scholars, making significant contribution to scientific research and higher education worldwide. Moving to the next part of the hybrid seminar, the next is the address by the guest of honor, His Excellency Ambassador Aftab Ahmed Kokar, Assistant Secretary General, OIC Jeddah.
Bismillah ar-Rahman ar-Rahim. His Excellency, the Coordinator General of Comstech, Professor Muhammad Iqbal Chaudhry, Honorable Dr. Ziaur Rahman, Director of A.Q. Khan Institute of Materials and Emerging Sciences from the Quaid-e-Azam University, Honorable Dr. Muhammad Ibrar Shanwari, Associate Professor representing International Islamic University's Department of Environmental Science, distinguished guests, esteemed academicians, dear researchers, and the students. It is an honor for me to welcome you all at the OIC Comstech Secretariat. Today's seminar, titled Climate Change and Environment Sustainability, a multidisciplinary approach to energy for climate action, is an important opportunity for all of us to know about the issue. Climate change is no longer a future forecast, but a present-day reality in the form of floods, rising temperatures, melting glaciers, contaminated water, low air quality index, and energy crisis across the OIC member states. Yet, within this challenge lies a transformative opportunity, and the core of climate action is energy specifically, a multidisciplinary approach to energy that transcends engineering alone. Our 57 member states face a unique energy dilemma of security, equity, and environment sustainability. While some are leading producers of hydrocarbons, many remain energy poor, with over 800 million citizens across the OIC still lacking access to clean cooking facilities and reliable electricity. Therefore, our multidisciplinary approach demands that we decouple economic growth from carbon emissions without sacrificing industrial development. However, it soon became clear that science and technology alone could not provide the solutions for averting or partially alleviating the negative consequences of global warming and the conflicting objectives of economic growth, affordable prices, and sustainability. What we are experiencing today is a real evolution that is transforming the global energy sector and hence the global economy. It impacts all aspects on how we generate, distribute, and consume energy. This revolution is not just a technological process, it is first and foremost a societal and political process in which technology is one determining factor. Thus, the role of different stakeholders, as well as societal needs and wants, and the policymakers are to be duly taken into account for the transition to be timely and effective. International agreements, as well as small and large-scale infrastructure projects to support the transition phase, all need to be based on a clear vision of the future and require laborious dealings and negotiation skills. The positive echo from the scientific community, reflected by the number and the quality of the contributions submitted, proves the significance of this general approach and the necessity of examining energy issues from a more general perspective, which should increasingly become part of the general public discourse and discussions beyond the strict framework of academic debates. Society at large needs to be actively involved in developing, suggesting, supporting, and implementing possible and sustainable pathways, which are relevant at both the national and international levels. This will give the decision makers the confidence and sense of urgency to develop and implement necessary policies. By bringing together expertise from fields such as environmental science, engineering, and policymaking, we can develop comprehensive solutions to mitigate the impacts of climate change and foster a sustainable future. Let us turn the energy transition into a renaissance powered not just by the sun and wind, but by the collective will of 1.8 billion Muslims. The world needs a just transition, and the OIC will lead it. Thank you.
Thank you for the address, on the Chief Guest address of His Excellency Ambassador Aftab Ahmed Kokar, Assistant Secretary General, OIC Jeddah. Moving to the next segment of this seminar, for the keynote address, I would like Professor Dr. Ziaur Rahman, Director, A.Q. Khan Institute of Material and Emerging Sciences, Department of Chemistry, Qaid-e-Azam University, Islamabad, for his keynote address.
Assalamu alaikum wa rahmatullahi wa barakatuh. To everyone present here and to those who are online, I express my deep gratitude to Professor Dr. Muhammad Iqbal Chaudhry, Coordinator General OIC Comstech, Islamabad, and to Ambassador Aftab Ahmed Kokar, Assistant Secretary General OIC Jeddah, and Honorable Dr. Abdul Halim Asghar Saab and Mr. Muhammad Tufail for inviting me to present my perspectives and group findings on the topic climate change and environmental sustainability, a multidisciplinary approach to energy for climate change. Today, I will discuss with you conversion of the formic acid into hydrogen, a step forward in combating climate change. Let me first ask you guys a question. Everyone here is familiar with the photocatalysis, or should I start it from the very beginning? How many are familiar with? Okay. So few. So let me start with the saying of the Stephen Hawking, one of the brilliant scientists of the era. According to him, there are three big threats to the modern civilization: nuclear war, and artificial intelligence, and climate change. And the Stephen Hawking key aspects of climate change are mentioned here. Stephen Hawking viewed global warming as one of the greatest threats to humanity, warning in 2017 that Earth was approaching a tipping point where climate change would become irreversible. This is the dangerous point. He feared and often cautioned against uncontrolled emission turn Earth into a giant ball of fire, similar to Venus, with the temperature reaching 250 degrees centigrade. So of course, it will not be any more inhabitable. Hawking frequently warned that humanity must act swiftly to reduce emissions, emphasizing that this was a crucial test for humanity. Now, what is needed? He linked climate change to the other existential threats, as I said, to the nuclear war and artificial intelligence, arguing that humanity needs to colonize other planets within 100 years to survive, as our own planet becomes increasingly precarious. So the point is, either we will have to move from this planet in 100 years to some other planet, or we need to take a swift action. So first, let me explain you the concept of climate change. When there is a longer shift in temperature and weather patterns, so that kind of shift, we call it climate change. And this climate change is because of certain gases. That is, actually, we are relying on the fossil fuel for our energy needs. So what is the problem with the fossil fuel? It releases carbon dioxide, right? And this carbon dioxide actually is a greenhouse gas and increasing the temperature of the earth. And some other gases as well, that is nitrous oxide and methane as well. So because of that, the temperature of the earth increased by 1 degree Celsius so far, and this will be going on increasing. Now, this slide shows the major percentages from the industry of the carbon dioxide from the industry and from the vehicles. And additionally, we are doing deforestation. If you look at this point, let me just we are almost 32 million acres of the forest were lost annually. Yes. Okay. So if you look at here, 32 million of the forest lost annually from 2000 to 2010. So basically, the trees are actually the sink of carbon dioxide. So we are producing carbon dioxide and we are vanishing the carbon dioxide sink. So this actually increasing to the carbon dioxide level to the dangerous point. What would happen if the carbon dioxide level increases? As I said, carbon dioxide is soluble in water. And this solubility actually turns the water acidic in nature. And when the water acidify, that will be detrimental to different kind of plants. So vegetation will no more survive. Some of the plants would not survive. And secondly, it will increase the temperature of the water, and as well as it will result in glacier melting. That will result in flood, right? As I said in this slide. And now simple the mechanism of the global warming caused by the carbon dioxide. When the sun radiation strikes the earth and when it reflects back, So if the carbon dioxide, if you calculate the molecular weight of the carbon dioxide, it's almost 44, heavier than air. So it lies on the lower level of close to the Earth's surface. So when the radiation is coming out, it is absorbed by the carbon dioxide, and that absorption actually increases the temperature of the Earth. Now, let me share with you the air quality in terms of carbon dioxide concentration. So if the concentration of the carbon dioxide is between 1600 to 2100, so we call it a bad air, heavily contaminated air, and ventilation is required. Mediocre contaminated indoor airs is from 1500, the yellow one that you can see here. This part. So if we are in this zone of carbon dioxide concentration, so again, ventilation is required. This below 1000, the region is safe, right? So now the toxic carbon dioxide concentration, healthy, and the 350 concentration to 700 concentration is okay for human life. And when it is reaching 1000, so you will feel sleepy. And when it is 2500, so it is very bad for health. And if it is 5000, so you can't survive more than 8 hours in that environment. Now the question is, there are two kinds of strategies we can deal with the carbon dioxide. Number one, to stop carbon dioxide conversion, right? To stop carbon dioxide production. And second, carbon dioxide trapping and conversion. So these are the two strategies. So how to stop carbon dioxide conversion? We need energy transition from fossil fuel, the carbon dioxide producing fuel, to non-carbon dioxide producing fuels like solar energy, wind energy, hydroelectric energy, and tidal energies, and biomass energy. Secondly, we can switch from the normal engines to the electric engine, right? So this will also reduce the carbon dioxide level. So these are the two strategies by which we can stop the production of the carbon dioxide. Now switching to the strategies in which is we trapping either carbon dioxide or converting it to some value-added product. So the first thing is the nature help us in terms of carbon dioxide. As you can see, that you are all familiar with the concept that when the carbon dioxide is absorbed by the trees, it is converted into value-added product through photosynthesis. So and as a result, oxygen is produced. So this is one of the ways. So we can deal with the carbon dioxide by afforestation, planting new trees, or reforestation, restoring old ones, right? And the other things related with the technology. Number one, direct air capture that we call DAC, use chemical process to scrub carbon dioxide directly from ambient air for underground storage. Second, carbon dioxide capture and storage, CCS that we call, prevent carbon dioxide from leaving industrial smokestacks in the first place. So these are actually the materials that we use for carbon dioxide storage, you can say. And these are normally porous. So what is the criteria for those materials? When there is a porous, so this porous should be polar in nature. The inside of this pore should be, because carbon dioxide is polar in nature. So to trap this in this pores, so the pores inside should be polar in nature. Now, the next strategy is the conversion. This is one of the important strategy because you are converting carbon dioxide, the dangerous things, to value-added product. For example, and this process normally involves catalyst because it is high activation energy process. So catalyst is required to convert carbon dioxide into ethanols, formic acid, methane, ethylene, and some other kind of polymers, etc. And this is the chemistry of all those conversions. You can see the number of electrons involved in each steps and how much economy per ton expenses are there. Profit is there. Now, as a strategy as I said, the energy transition is one of the strategies to stop carbon dioxide production. So the hydrogen economy or the hydrogen production is one of those strategies. When hydrogen is used as a fuel, its combine with the oxygen, form water. And water is beneficial for us. It's not harming the environment. So this actually reduces the carbon dioxide. So hydrogen can be considered one of the alternative fuel to the fossil fuel. However, there are certain production challenges. You can see at the bottom of this slide over here. The different steps are involved: convergence, purification, compression, because it is a gas, and transportation, right? And there are certain challenges. And this kind of hydrogen production, you can see the cost is high, right? And it requires like some technological challenges are also there, because you are needing catalysts, and there are certain criteria for a good catalyst, of course. And there is also safety concern as well to the production of hydrogen and usage. Now, we can store the hydrogen in three ways: by compressing the gas storage, okay, and then we can liquefy it, and then the other things is we can store it in certain chemicals. And for the hydrogen is a non-polar gas, so you need a porous material from the end. The pores of that material should be non-polar from the inner side, right? So in that case, only the hydrogen can be absorbed. Of course, there are again certain challenges, because hydrogen, you need minus 253 degree temperature to liquefy it. It's too high. And you need high insulation to maintain that temperature. And of course, hydrogen actually damaging the metals, because hydrogen sometimes convert metal into metal hydrides. And of course, it is lighter gas. It can, the volumetric density is small. So the number of molecules in the given area is smaller. And there is leakage of risk as well. Okay. Now, one of the strategy to convert this, the strategy for hydrogen storage is to convert it into the formic acid. Formic acid is a liquid, so we can easily store it. And you can see here, this is the mechanism of okay. So now you can see here, this is the hydrogen storage. You catalytically combine this with the carbon dioxide and convert it to formic acid. Formic acid is a liquid, as I said, so it can be easily stored. And now in the next step, when you are looking to use it as a fuel, so you need a catalyst to convert this formic acid into hydrogen and carbon dioxide. So core chemical pathways, electrochemical pathways of carbon dioxide conversion. You can see here 2-electron process and formic acid is formed, and catalytic hydrogenation process, in which carbon dioxide and hydrogen is combined in the presence of catalyst. That may be a catalyst or photocatalyst, depending on the situation, to convert it into formic acid. Now, formic acid, as I said, is a liquid at room temperature and serve as a highly convenient medium for hydrogen storage. And rather than compressing hydrogen gas, the liquid acid can be easily transported and processed back into hydrogen and carbon dioxide when energy is needed. Formic acid can also be produced from the biomass. There are certain steps involved, like biomass is hydrolyzed to sugars. You can say the right-hand side, there are certain steps. And sugars are dehydrated to HMF. And HMF is oxidized to formic acid, and formic acid, the outcome of formic acid can be used as a fuel. And there are the reactions you can see over here. So now the conversion of formic acid happens through two parallel pathways: dehydration pathways, in which water and carbon monoxide is produced. And you know that the carbon monoxide is pi acceptor, and it can stabilize metal in the zero oxidation state. So if you are using a catalyst, it will combine with the catalyst to form metal carbonyl. Secondly, this is a unwanted pathway. And second one is the dehydrogenation pathways. That is thermodynamically favorable, because if you look at the energy, here this step required gives me energy of minus 28.5 kilojoule per mole, and the other one require minus 48.8. So the most favorable is the dehydrogenation pathways. So we should design a catalyst that favor the dehydrogenation pathways instead of dehydration pathways, right? So now diagnostic points so far: converting carbon dioxide and hydrogen to formic acid is a promising carbon utilization technology that turns greenhouse gases emission into chemical feedstock or liquid fuels. The process requires a catalyst. Catalyst should preferentially convert formic acid into carbon dioxide and hydrogen, as I said, dehydrogenation pathways, and should deter carbon monoxide plus water conversion process that we call dehydration pathways. Catalyst should be efficient, stable, and cost effective. Before going to the concept of photocatalysis, you must have a clear picture of the solar spectrum, because in the photocatalysis, the efficiency of the catalyst depends on the number of protons absorbed. In the solar spectrum, UV make a smaller portion of 3 to 8%. Visible light form 42% of the solar spectrum, and infrared form 49 to 55% of the solar spectrum, right? So this means the UV catalyst is not a suitable catalyst because it will absorb lesser number of protons. Number of protons absorbed are lesser, so lesser number of electron hole pairs would be generated. And if there are lesser number of electron and hole pairs, so the substrate will receive lesser number of electron and holes. So now what to do? What should be the good catalyst? For a good catalyst, it should be good light absorbing capability. The visible active photocatalyst is preferred over the UV light active photocatalyst. Low rate of electron hole pair recombination. Suitable band edge positions for redox reaction. Because redox reaction is happening, the electron is always moved from negative reduction potential to positive reduction potential, right? So this should be stable under mild condition and should be economical one. So cadmium sulfide is one of those examples. It is cheap and visible light driven catalyst, but the problem is the whole electron hole pair recombination is higher, and it is unstable, is susceptible to photo degradation and photo corrosion, in which the holes eaten up the cadmium sulfide and oxidize it to sulfur, as you can see. So the cadmium is leaching in the system. That is not good. So keeping in mind all those things, we were planning to design a catalyst that can absorb, that is cheap, visible light driven, and that is stable enough. So we opted the cadmium sulfide, but we modified the structure, and there are certain steps involved. First of all, we take the sodium hydroxide and combine it in 1:1 mole ratio with butyl amine, and carbon disulfide was added to convert this to sodium dibutyl carbamide thioate. And this material was then combined with the cadmium nitrate to convert this into the complex form, as you can see. I will not going into detail of that. And then this cadmium complex of the dithicarbonate was decomposed in the ethylene diamine solvent. So you can see here, you can decompose in the presence of this solvent at low temperature. So this decomposed this cadmium sulfide at 118 degrees centigrade to cadmium sulfide nanorods. And then we modified this cadmium sulfide nanorod. We photo-deposited nickel over the system, because if you look at the reduction potential of the valence band and the nickel, so the valence band reduction potential is, so the valence band potential of the cadmium sulfide is more negative than the nickel. So nickel can be used to trap electron during the process. And similarly, the cobalt chloride was used in the solution form. So chloride was used as aqueous catalyst or homogeneous catalyst, and nickel was used as heterogeneous co-catalyst, right? And this is the mechanism of that reaction. And you can see during the process, the H2S is released. So if you are carrying out this reaction, just direct the H2S gas to some other flask and put lead nitrate in that solution. If lead nitrate turns into blackish lead sulfide precipitate, this means the reaction is going on. Now, these are the XRD and TM and HRTM images of these cadmium sulfide nanorod. You can see the crystalline nature of the nanomaterial because we have a broader and sharp peaks. So it is nano size and crystalline in nature. And this XRD pattern is for the hexagonal quartzite structure. And if you look at HRTM images, you can see the nanorods stay together in this, right? And if you look at HRTM images, you can see the clear edges. This means the system is, the material is crystalline in nature. And furthermore, the SAED pattern, selected area electron diffraction pattern, you can see the clear pattern, diffraction pattern over here that also explain crystallinity of the material. And the latest distances, the 0.37 and 0.67, that correspond to 001 and 100 plane, that is also observed in the XRD. So this means the material is in nanorod form with the, if you look at this, the size of this diameter of this nanorod is 7 nanometer and the length is 80 nanometer. And you look at this HRTM image, you can clearly see the nickel deposition over here, the circles, these black spots, right? So nickel is photodeposited. And now the nickel, you can see here, the nickel is present in two forms because we didn't use the inner condition. So nickel, you can see in the XPS two kind of peaks for nickel oxide and nickel hydroxide. And the steady state system, if you look at, one thing is clear, this is the emission spectrum, means when the electrons getting baked to combine with the holes. So this spectrum is the emission spectrum. So if the intensity is higher, this means the recombination is higher. And if the intensity is lower, this means the recombination is lower. If you look at the four catalysts, the cadmium sulfide nanorods, cobalt modified cadmium sulfide nanorod, nickel sulfide cadmium sulfide nanorod, and cobalt nickel sulfide cadmium sulfide nanorod. So you can see here, this is with the small intensity, this means the recombination is lowered. And same is proven by the time resolved PL decay curve. You can see here again. Next step was optimization of the catalyst. You can see here when you are increasing the cadmium sulfide concentration in solution, photocatalytic activity increasing, but at certain point, after a certain point, it goes on decreasing. This we call the optimized point. So the concentration here is 1.04 mm. And similarly, we optimize the concentration of the co-catalyst, and you can see here, this is the optimized concentration 1.25 with the higher hydrogen activity. Similarly, is true for the cobalt, that is 0.75 millimolar concentration. And you can see the activity, the highest activity was observed for this one. So we have 1.04 millimolar cadmium sulfide, cobalt 0.75, and the previous one 1.25. And this is the picture format, the graphical format of the whole discussion. You can see here, this one is for the nickel one. You can see here, the optimized point, and this one is for the cobalt one here, somewhere here. And now the next step is the photocatalysis. So the photocatalytic reactions was carried out in photoreactor. And this photoreactor was initially purged with nitrogen for 20 minutes. And when this cadmium sulfide, the catalytic system was shined with the visible light, so the electron hole pairs was generated, and this electron hole pairs convert the formic acid into hydrogen carbon dioxide. And you can see here, when you are using this cadmium sulfide alone, so the amount of hydrogen produced was 1.34 millimole. And when you are combining with the cobalt, so 14.2 millimoles. And when you combine with nickel, so 28.8. And when you combining with cobalt, nickel both, so the production of hydrogen increased to 32.6 millimole. So I will explain why this happens in a while. So furthermore, analysis of the evolved gases by the gas chromatography revealed that the carbon dioxide hydrogen ratio remained below the theoretical value 1:1. If you look at the conversion of formic acid, so the carbon dioxide and hydrogen should produce in 1:1 ratio. But the problem is carbon dioxide is soluble in, so the ratio is not exactly the same when you are analyzing with the GC because of the solubility of the carbon dioxide. And secondly, in addition, when a base trap containing 10 molar sodium hydroxide was employed to capture the carbon dioxide from gas mixture from the catalytic reaction, nearly 50% reduction in volume was noted because it is converted to sodium carbonate and water. And the GC analysis of the gas treated with the base trap also confirmed the absence of CO. Initially, I said that the CO step that we called hydration step, that should be avoided. So you can see here, when we analyze those gases from GC, no traces of carbon monoxide was observed. So now this catalyst is stable enough. So we carried out the long term experiment, and we used the catalyst for almost 18 hours, and we recorded the hydrogen concentration after 3 hours each. You can see 3, 6, 9, 12, 15, and 18. And you can see here with the passage of time, the amount of hydrogen release was increased, reaching a maximum value of 285. And this is equal to the number of 1.06 10 raised to the power 5 after 18 hours. That is very, very significant. If you look at the literature, so it's very high. That is why this paper was published in ChemSysChem. So now do the comparison with the other catalysts. And in the start, I said that we should reduce the cost. We should make the process more efficient, right? So you can see here, if you look at this system, it's containing cheap metals. Of course, the cobalt is a bit expensive, but less expensive than the palladium and the platinum one, right? And the nickel is very cheap. The cadmium itself is very cheap. So this is a cost-effective catalyst as compared to these two. You can see the palladium one and the platinum one. This one is UV-driven catalyst, and this one is visible light-driven catalyst. If you look at the hydrogen activity, you can see here it is 17.7, and our case it is 32.6, much higher than this. And in this case, the platinum one, we have 4.46 from the literature, and we have 32.6. So we have improved the activity of the catalyst, and we have reduced the cost. So now, let me explain the whole thing, why the catalyst is so active, and what was the concept behind designing this catalyst. As I said in the start, that this we call, these are the photons. So if it's visible light, so as I said, it's 44% of the solar spectrum. So more photon will fall here. More photon here, so more electron will be generated. The electron will jump from here to here, the whole, and more electron will be generated. And if we are using here, what would happen if we are using this alone? No this here, no this here. This will actually eat up this sulfur and convert it into sulfide into sulfur. And this we call photovoltaic or photo-oxidation of the cadmium sulfide, right? So we are scavenging this hole with the cobalt. If you look at, this is more positive than this. So the cobalt is oxidized to cobalt 3. And then this state electron from the format ion. And the format ion converts this cobalt back to cobalt, and the process is continued. That is why the system is stable. And on the other hand, on the nickel one, if you look at the edges here, right, this one.
So this edge is more negative than this nickel one, nickel oxide or nickel hydroxide. So the electron moves from this valence band to this nickel, and from the nickel it reduces the proton to hydrogen. So this whole system actually improves separation and mobility of the protogenerated electrons, enhance the catalytic activity, enhance the stability and tolerance to the proto-oxidation. And this strategy is applicable to other catalysts as well. You can use, instead of cobalt, some other catalysts, maybe organic in nature, maybe inorganic in nature, whose reduction potential lies just above here. And you can use any other catalyst, key catalyst, that may be organic or inorganic in nature, whose reduction potential is less negative than the valence band of the cadmium sulfide. So these are the publications. This is the review, the cover page, and this is and also how we can modify these catalysts. So on the basis of this, just let me allow to give you the perspective of this whole discussion. So you can do three things major. You can change the co-catalyst system. Number one, the nickel one. There are multiple options available. You can play with the cobalt kind of materials, and you can change it with the organic something, or you can use any other metal ions that is easily oxidized and reduced, And third, you can combine this nanomaterial, this cadmium sulfide, with some other materials with this kind of arrangement. This is the valence and conduction band of the other material. This is the valence and conduction band of the cadmium sulfide. Or we can do it like this. So we can go in both ways. So we can either make the composite, or we can use different kind of co-catalysts like nickel, platinum, palladium, or we can use other metal ions like cobalt, maybe iron, maybe some other inorganic. You can make use of the XPS, and you can make use of the electrochemical techniques to find out the bend edges of the materials. Or you can theoretically find it out, the homo-LOMO of if you are dealing with the organic one. So this, by this way, we can modify the catalyst and we can make it more beneficial for the formic acid cycle to convert carbon dioxide to formic acid back to hydrogen, and we can use it in different manners. Thank you very much. I'm here to take any question. Okay.
Thank you so much, sir, for your comprehensive keynote address on the carbon dioxide capturing, storage, and hydrogen production and green initiatives for sustainable energy. Moving to the last keynote address, I would like to call upon stage Dr. Muhammad Ibrahim Wari. He is Associate Professor, Center for Interdisciplinary Research in Basic Sciences, Department of Environmental Sciences, International Islamic University, Islamabad.
Bismillahirrahmanirrahim. First of all, I would like to pay thanks to the comstech team who organized such learned seminar for students and faculty members. As far as my talk is concerned, I have taken a little bit general and basic approach. So let us know what is climate change and environmental sustainability with the aspect of multidisciplinary approach to energy or climate change. The purpose of this talk is to learn about climate change basics, energy climate link, sustainability and SDGs, multidisciplinary roles, and research and campus actions. So this is the core message of this presentation. Climate action needs evidence, technology, policy, finance, behavior change, and institutional leadership. As far as the context is concerned, why climate change matters? So we all know that the present incidences of heat waves, floods, food, water, and health issues are the main concern which are linked with climate change dilemma. While understanding the climate change, some basic concepts is there. Weather, by weather we mean short-term conditions, today's temperature, rainfall, or wind. Climate, long-term pattern of weather over decades. And climate change, long-term shifts in temperature, rainfall, sea level, and extremes. Human activities have increased greenhouse gases, strengthening the warming effects. Energy is at the center of climatic action. So this is the link of energy with the warming impact. Fossil fuel use, greenhouse gases emissions, and then the effect is in the form of warming impacts. You know all that electricity, transport, heating, cooling, industry, and agriculture all depend on energy. Cleaner energy systems can reduce emissions while improving energy security. Energy choices affect affordability, air quality, jobs, and public health. As far as the environmental sustainability is concerned, meeting today's needs without compromising the ability of future generations to meet their own needs. Energy is required clean and reliable form. Water conservation is the utmost need. Cities should be built by green buildings, or the buildings of the cities should be converted into green buildings. Energy, low carbon energy should be utilized in the industry. Education awareness is needed, whether they are students or they are general public, while biodiversity is also need of the time to conserve. As far as the solutions are concerned, energy for climate action, renewable energy, energy efficiency, clean transport, green buildings, storage, smart grids, policy, and behavior change. Climate action is a portfolio of solutions, not a single technology. As far as the technologies are concerned, so renewable energy options, we have solar, wind, hydropower, biomass, and geothermal. As far as the local relevance is concerned, in Pakistani context, Pakistan faces higher exposure to floods, heat waves, glacier melt, droughts, water stress, and air pollution. Clean energy can support climate action, energy security, and reduce import dependence. Universities can help through local research, testing, policy evidence, and community outreach. So there is a local question, research question, which buildings waste most energy? Where is solar most viable? How do people accept clean energy changes? Make it local, measure it, and improve it. As far as the collaboration are concerned, it is a multidisciplinary approach. Engineering, systems, economics, finance, policy governance, health risk, social science behavior, computer science, data, AI, agricultural adaptation, education awareness. So energy for climate action. No single discipline can solve climate change alone. As far as the academic action is concerned, role of universities and researchers, applied studies on local energy and climate problems is need of the time, while teaching climate literacy across disciplines, energy audits, solar waste, and procurement, policy support, evidence for government and industry, students' projects, startups, and prototypes are needed in this respect. As far as the research opportunities are concerned, rooftop solar performance, AI-based energy demand forecasting, climate smart agriculture, green library, green campus models, energy audit of campus buildings, heat wave, and public health impacts, public perception and renewable energy, policy evaluation and green finance. Good climate research is measurable, local, interdisciplinary, and usable by decision makers. As far as you know, that nowadays there's a lot of emphasis on solar energy. But do you know that after expiry of the solar cells, where will they go? They will go to the environment. Do you have any dispose of technology of these solar batteries, storage batteries, or solar cells? No. This is a question for future. But by research and various reverse engineering methods, we can get a solution. As far as the energy efficiency is concerned, energy efficiency reduces bills and emission immediately. It often costs less than adding new generation capacity. Simple actions include LEDs, efficient fans, AC temperature control, insulation, smart meters, and shutdown routines. So the cleanest energy is the energy we do not waste. Just energy transition. So as far as the equity is concerned, a clean transition must be affordable and inclusive. Workers need reskilling and new employment pathways. Vulnerable communities should not carry the cost of transition. If we look on the global agenda, climate actions are linked to these SDGs. SDG 7, clean energy, SDG 11, sustainable cities, SDG 12, responsible consumption, SDG 13, climate action, SDG 3, health, and SDG 15, life on land. So these are some practical actions which are needed to the institutions to be taken. Audit, measure energy use. LEDs replace inefficient lighting. Solar install where feasible. Policy green procurement. Waste reduce the recycle. Mobility, carpooling and shuttle. Native trees and aftercare. Sustainability and monitoring. So what kind of individual action is needed? Save electricity and report wastage. Join environmental clubs and awareness campaigns. Develop clean energy projects and research ideas. Use public transport, carpooling where possible. Reduce single-use plastics and paper waste. Support plantation with long-term aftercare. So the second part of this sentence is very much important, which is almost lacking. So for this, students can move from awareness to action to innovation. So this is which is the responsibility of the students. As far as the barriers are concerned in this regard, these are the challenges in energy transition. Financing, upfront investment is needed. Storage, backup batteries, skills, trained workforce, equity, affordable access, grid capacity, solar, wind integration, policy gaps, regulation and incentives, awareness, behavior change, and data monitoring and evidence is needed. Barriers are also research opportunity. So these are the different parameters on which students can focus their research in near future. What is the action pathway? The way forward? Measure, reduce, replace, educate, innovate, and monitor. So this is the path of action we should take. Now coming towards the closing discussion, as faculty, students, and researchers, we are not only observers of climate change, we are contributors to climate solutions. So my discussion question is, how can our institution reduce its carbon footprint through energy efficiency, renewable energy, and behavior change? These are some references. Thank you very much for your patience.
Yeah, any such question on this? Thank you, Dr. Muhammad Ibrahim for the detailed presentation of the climate smart agriculture, energy efficiency, clean transition, explaining different SDGs were actionable. Thank you to all the audience and our speakers. Now, moving to the next segment of for the question answer session. Before the question answer session, I would like Professor Dr. Mudassar Israr to share some words with the audience regarding the climate change. Professor Dr. Mudassar Israr.
Bismillahirrahmanirrahim. Honorable speakers and discussed of my dear colleagues and students, I'm thankful to you for joining us here. And my special thanks are to the speakers. They are actually the core of this seminar. They are the leaders of climate change, how to tackle this matter. This matter is actually going to engulf this world very soon if we are not going to take it seriously. So I'm thankful to them for advising us. how to tackle the issue, and hopefully we'll take some practical measures, and we should join hands, and comstech is always there to sort out this problem. Climate change actually is the issue of climate change is directly related to our lives. Initially, basically from our daily life. If we change our routine, if we stop wasting things, if we start conservation of materials, especially biodiversity, we take care of plants and start forestation instead of deforestation, then we are going to help and save this earth. So I'm once again thankful to all of you for your participation.
Thank you, Professor Dr. Mudassir Ishaq. Before concluding the session, we have a question answer session from the here. Yes, sir. The question must be very specific for the speaker. Someone want to ask question? Yes.
Mr. Hawking, sorry to go back to my speakers. One of who is in phase 1 of our teachers from guidance and chemistry. Thank you so much for a very thorough and insightful presentation. My question is to Dr. Gibran, actually. So, given that you are an expert on climate elections, and I'm also a researcher working on the renewable energy resources. So, what do you think that which renewable source has the more potential in future? And also, do you think that this sort of agenda that the wealthy countries or climate compensation to developing countries? So I'm just curious to know what are your opinions on both of these questions. Which one has a more potential in future? And do you think that wealthy countries owe compensation to the developing countries? Thank you so much.
Very good question. Thank you very much. As far as recent development is concerned, I think there's a strong potential for renewable energy pipeline plants. You know that 90% of the production is going on this and that can be converted into various kind of photocells. You can also work on artificial photosynthesis process you can use, and various kind of technology can be developed. You can genetically modify the energy for this purpose, and there's a strong potential of this as far as your second part of the question, that how developing countries can cope with this problem with collaborations. You can rely on your indigenous research, how to convert this resource into energy. And another important opportunity is to convert waste in energy. So waste is not waste, it is a resource which can be converted into energy. So in Pakistan, it is much more needed. On terrestrial land, you can convert waste material. So these are the two major aspects on which our students can work and make some prototypes for the industry. In China, actually, the waste is sent out by the consumer. Yes. This is my personal experience. When I was doing my postdoc in Japan, when we give the waste on every month, money comes to your account. This is your waste.
Next question.
I have a question to Dr. Ibrahim and Dr. To both of you. I am a PhD fellow in climate change in West, and in my second year of research, and I'm working on the material for carbon everything, and it's a life cycle assessment. I have a background, the industrial background in textile industry and pharmaceutical industry. To Dr. Gar, I wonder that the capitalists and the industrialists are not ready to listen. I talked to 2 3 owners to work on the green energy. They said it is very expensive, we cannot work on. On the other hand, they are earning, they are benefiting from like polluting the air and the water both at the same time, especially the textile industry. They are polluting the air and the water both, but they are not ready to listen, and especially the small industries. And in addition to that, our bureaucratic culture, like when the companies go to them for financing or taxing, there is a thing going on like bribery and other things. So how can we change these behaviors, like in industries?
Thank you very much. Another very good question. Actually, how you will convince the industry is very good question. Do you have any carbon credit system in your country? No. And this is the system which will compel the industry to make sure that they are not harming the environment. One of my PhD students recently, she started work on it to explore the carbon credit potential of Pakistan and then to make a roadmap towards MRV system, monitoring, verification, and evaluation system for that. That is the only solution towards this problem, that industry will be compelled to purchase carbon credits for their product delivery. So I think there's no other way in this regard. So we should have a carbon credit authority, and they properly observe, or they have a system, and we can make a digital system out of it. And they can clearly observe emissions of the industry and their environmental degradation they are causing, and then they have to pay the cost of that. So I think that is the only solution in your future. Thank you.
Thank you so much. And Mr. Yeah.
Sometime back, I work as expert on material and design emission. So I was part of the panel, and I suggested that everything you are asking from the academia and researchers. Why you are not asking from the industry? You should make a policy. They can compel the industry to understand and R&D, right? So I think this question is related to the work. We need a policy, certain policy. They compel the industry, and they should allocate certain budget. And every country there are certain budget for this R&D, but sometimes 5%, some depending on the GDP, right? 3% and maybe more. So I think if the government take a step in this direction, so it will be beneficial for both industry as well as the research, because we will give some feedback on some of the process, we will make it more efficient, and of course it will save money and very good year economy as well.
Yes, sir. I think the academia, the government, and the researcher,
Yeah.
all three together, they can work on it. Sir, I have a very special question to you. That research, I think, done back in 2017 or 18.
Yeah.
That related to nano one dimension material. Sir, nowadays people are making material and working on its self life cycle assessment. Either the materials are sustainable or not. So have you ever done the LC on the nanorods or not? And like these materials are itself are sustainable, because let me complete for you around.
Yeah.
Because when you go into the experimental setup, instrument consuming electricity, and electricity nowadays coming directly from the fossil fuel. So if one way or the other, at one stage we are capturing the carbon, but back in the deep down, we are also emitting the carbon in the atmosphere as well. So there is a life cycle assessment technology nowadays where we work on it both on the experimental part and on the material part. So this is the a very major loophole in our researches nowadays. So have you done on LC on the nanograph? No, not. How much is that? How much these are sustainable to the environment? Life cycle system.
We did, but like, your question is related to two things, right?
Two things.
Yeah. So one thing is that in this dunya, nothing is immortal, right? You can talk about the longevity of certain systems, but there is end for each and everything, right? And if you look at the nanorods, are just one of the parts because of the shortage of time. You can do the assessment whether the cadmium is leaching in the water or in the system or not. You can follow that, and we followed it, and we observed there is nothing at least for 18 hours. So as I said, you can achieve longevity, but you can't like make it immortal. Sustainable for all time, right? So there is limitation in terms of material design.
So then, sir, yes, I know about it, that the limitation is the 1T and the 2T material, but what about the MOFs? Uh, Today MOFs are very in the market for the carbon capture and then utilizing or the converting it into formic acid or the ethanol to like this. And the studies are now initiated on its life cycle support. And these studies have proven that the MOFs are much better than the 1D material. So I think, and I observed this in our whole academia. Like I've done MPhil in University of Agriculture and bachelor's in University of Sargodha and now in last in all three degrees I work on material. But there is a still major loophole exist in all the academic centers where they are making the materials, but they are not working specialized working on those material, other these material, how much these are sustainable to the environment itself. So I think we can go towards studying the life cycle assessment of the material, so that we can prove that the working on material by the chemistry scientist or the physical scientist mean to say that they have to come with an evidence that really we are working. Because last year I was sitting with an company owner and he was saying, you guys are working, but there is no evidence that you guys are working. Show us working. These research articles are not that much productive or not much evidence to prove us the evidence. So I think this is the way we can prove to the nations and to the industrialists that the material that we are making for reducing the GHGs from the environment or the direct air capturing, these materials are very efficient and they can use it. And sir, one another thing.
Dr. Saab, we can also discuss
Just,
on the in the tea
I'm
break.
just concluding.
In the tea break.
The textile industry, sir, they can reuse their work, but they are just polluting it. This is one another issue that where the academia, the researchers, and the government can work on it.
Okay, let me briefly answer to the question, right?
Thank you.
Sustainability is of course important, and this is a part of your question. And you asked about the material that you are more interested in, more, of course. Home is very good, but the applications, what kind of application you are looking for, there's matter. What kind of material you need to use? For example, you are dealing with the complex set. So I would suggest like copper type material is more good for their purpose because of the certain reasons, right? And for the more, you are right, it is sustainable. But do you know the synthetic challenges of the more? Are all laboratory equipped with those challenges? That's the point. So your sources plus applications and plus limitation, and how can you take them with the current facility, those limitations? Yes, ma'am.
Thank you.
I hope I answered all the questions.
Thank you. To conclude this session, I would like Professor Dr. Mudassir Israr to present souvenir to our guest speakers. First of all, I would like Professor Dr. Ziaur Rahman to come in front of stage and
Online question, online request to make it. Request to come and online. Thank you very much.
Professor Dr. Muhammad Ibrahim Wari from Oxford.
Thank you.